Alright guys, so today we're going to talk about the kinematic equations. And kinematic equations are equations that you can use to describe motion as long as an object has a constant acceleration. So as long as the acceleration does not change, you can use the kinematic equations. And we're going to derive the equations today, and we're going to derive them from this velocity versus time graph that you see here. We can tell that the object has started with some initial velocity at time 0 and has increased to some more positive velocity after some amount of time t. And we know it's done it with a constant acceleration because the graph is a straight line. So the first equation we're going to look at is what we call our final velocity equation. And we're going to derive it very simply. We're just going to derive it from the slope-intercept form of an equation, which of course is y equals mx plus b. Okay? And so that equation gives us some point y at some other point x based on the slope m and the y-intercept b. So we're going to use that second point, tv, as our point. So our y value is simply going to be v. Okay? And as we learned in the last couple days, the slope on a velocity versus time graph is always acceleration. Our point that we would normally think of as the x point, or our axis that we'd normally think of as the x-axis, is actually time in this case. And then if we look at our graph, our y-intercept, or in this case our v-intercept, is actually what we would call v0. So if you want to know the final velocity of an object that's under constant acceleration, the final velocity equals the acceleration times the time plus the initial velocity of the object. Okay, so the second equation we're going to learn is an equation for displacement. So remember, for a velocity versus time graph, that displacement is always the area underneath the curve. And to find the area underneath the curve, I'm going to take this graph and split it into a rectangle and a triangle. Okay? And so my displacement, delta x, is just going to equal the area of the rectangle plus the area of the triangle. And so we'll do the rectangle first. The rectangle is v0 tall and t wide, so that's going to be v0 t. And then we're going to add the triangle. Okay? And the triangle is 1/2 times base times height, so we're going to do 1/2 times the height, and that height is going to be v minus v0, and then the base is going to be t. And then we can simplify that equation a little bit by doing a little algebra. So delta x is going to equal v0 t plus 1/2 vt minus 1/2 v0 t. So delta x then, if we have v0 t minus 1/2 v0 t, that's going to be 1/2 v0 t plus 1/2 vt. And then we can factor out the 1/2 and the t's, and we end up with delta x equals 1/2 v plus v0 times t. And so that's one of the equations we can use for the displacement for an object that's undergoing constant acceleration. We also have a second displacement equation that kind of comes from the work from the first two. So we had said earlier that v is always equal to v0 plus at, which we can rearrange to say v minus v0, or the change in velocity, will always equal at. And then for our work for the second equation, we said that delta x equals v0 t plus 1/2 v minus v0 times t. That goes back to the area under the curve. And so what we see here is that v minus v0 is equal to at. And so for this v minus v0 right here, I can substitute in AT. And I get that delta x equals v naught t plus 1/2 times at times t. And so, of course, a simpler way to write that is delta x equals v naught t plus 1/2 at squared. And so that's the second equation we can use for the displacement of an object under constant acceleration. Alright, we also have an equation for average velocity during constant acceleration. And we already know, and we've been talking about it since day one, that the average velocity of an object is always equal to the displacement divided by the time. But earlier, for our second equation, we also said that displacement is equal to 1/2 v plus v naught times t. And so if we take this value right here, we can plug it in for delta x. And so we get that v average is equal to 1/2 v plus v naught times t divided by t. And then, of course, our t's cancel out. So now we're left with v average equals 1/2 v plus v naught. So if we have constant acceleration, the average velocity will be 1/2 of the sum of the final and the initial velocity. But that's only true for constant acceleration, just like all these equations are only true for constant acceleration. Alright, so our last kinematic equation is another final velocity equation, but it's when we don't know the time interval over which the motion had occurred. And we're going to derive that using two equations we already use. One of them is the displacement equation, that delta x equals v naught t plus 1/2 at squared. And the other one we're going to use is that v equals v naught plus at. But we're going to rearrange that to solve for time so that t equals v minus v naught over a. And so we're going to take that value and we're going to plug it in for both of the t's in this equation. So when I do that, I get that delta x equals v naught times v minus v naught over a plus 1/2 a times v minus v naught over a times v minus v naught over a, since that t is squared. And so when I do that, the first thing I'm going to notice is that this a and one of these a's on bottom will cancel out. And so what I end up with now, after multiplying, since now I have an a on bottom of this term and an a on bottom of this term, I'm going to go ahead and multiply both sides of the equation by a, and so I get a delta x equals v naught times v minus v naught plus 1/2 times v minus v naught squared. Alright, and then the next thing I'm going to do is distribute some things out, and so I'm going to get that a delta x equals v naught v minus v naught squared plus 1/2 times v squared minus 2v v naught plus v naught squared. Then when I multiply everything by 2, I get 2a delta x is equal to 2v naught v minus 2v naught squared plus v squared minus 2v v naught plus v naught squared, because I've now gotten rid of that 1/2 as I multiplied everything by 2. So now that I've done that, I've got 2 v naught v's and a minus 2v v naught, so those completely cancel each other out. And I have a negative 2 v naught squared and a positive 1 v naught squared, so I can get rid of this 2 and that v naught squared entirely. So what I've been left with there is that 2a delta x equals negative v naught squared plus v squared. Add the v naught squared to the other side, and I got 2a delta x plus v naught squared equals v squared. And the final version of the equation that most people use is then that v squared equals v naught squared plus 2a delta x. And most people just leave it in that form and then rearrange it to solve for whatever they're solving for. Okay, so that's it for the 5 kinematic equations. When we get back to class, we'll talk about when to use each one, and then we'll start working some example problems with those.